Hey guys, welcome to Code Decode. In this video, we are going to look into the distributed transaction management and the ways to manage this distributed transaction, be it synchronous or asynchronous ways. So from synchronous, it's 2PC, 3PC, and asynchronous we have already covered, that is Saga design pattern. Now, let's start and see the 2PC first. Now, to start with, let's start what is a transaction. So a transaction is a series of actions that must be executed. If even one of the operation fails, the complete transaction must be rolled back. A transaction is something which follows the asset properties. So I'll give you one example. You are working with an e-commerce website. So you place an order. What happens first is the inventory is reduced so that another person should not see that particular product if the inventory was only one and you have taken it. So the first thing that has to be done after the placing of an order is to reduce an inventory. Then it should ask you for the payment, and if payment is successful, your order is placed successfully. Now this is a series of events and hence it is a transaction. Place an order, reduce an inventory, make the payment. When successful, make the order successful. So basically it should have a asset property being followed upon. Be it monolithic, be it microservice, asset properties has to be followed. So what is an asset property? It says A for atomicity, that is when we place an order for a particular product, the order service deducts the order quantity from inventory service and the payment service processes your payment. But atomicity makes sure that if the inventory is successfully removed but your payment is failed, that means your order is not placed successfully, then it is unfair to the other people to not to be able to place the order for that particular product which you did not have made the payment for. Hence, if you make the payment, then only the inventory should be reduced. If the payment is failed, order is failed, and hence inventory should again jump back to the previous state. So it's atomic in nature. It happens completely or it doesn't happen at all. Next is consistency. It says that your inventory should always remain accurate and consistent with the actual stock. Now suppose I have only one inventory for a particular product. Now what happens if you place an order? That is reduced to 0. In that case, your order will be accepted and you can make the payment and your order is successful. But what if you make for 2 quantity, but you have only 1? So the inventory becomes negative. So this is an inconsistent state because it does not make sure that you have an accurate and consistent stock, because -1 is not a consistent state of the system. So it makes sure that the inventory does not drop to the negative quantity. And hence in that particular scenario, you have to roll back the whole transaction because you have ordered the number of quantity which is more than the actual stock. So in that case, the transaction is rolled back, making sure that your system is consistent. That means you have not taken an order which is expecting you to have the quantity of product which is more than your actual stock in the inventory. So that makes sure that your system is consistent. The next is isolation. So when you have multiple consumers placing an order simultaneously, so suppose A is placing an order through order service, customer B is placing an order for the order service. Now, isolation makes sure that A does not see the immediate state of B and B does not see what A is doing in the system. So there should be no interference for the concurrent transactions. So A is doing something, B is doing something, A should not be able to see what B has done. B should not see what A has done, but at the end both tasks should be done. So isolation is nobody interferes in anybody's task. Durability says that after successful deduction of inventory and payment is processed successfully, the data is persisted in database. That means if I have one quantity of a product and if my order is placed successfully, my payment is also successful, the inventory should be made as 0 as the order is successful and payment is also done. If in that particular case, once the payment is also successful, inventory is also reduced to 0 and order is also successful, if this time, after all these things are done, if the system crashes and if it comes back again to life, then it should not show any inventory for the previous product. It should be 0. So after a successful completion of a transaction, the data should be persisted properly in the database or your hard disk. It should not roll back in any case. So in the case of system failure or the restart, the committed state is recovered from the durable storage, be it database or be it hard disk, and the system resumes with the consistent and correct data. That means you have a durable data. So these were 4 asset properties. Now next is how the transactions are different in monolithic and microservices. So in traditional monolithic, all this happens like placing an order, reducing an inventory, making the payment, and placing an order as successful. Everything happens in one single database. So the transaction boundary starts in your business layer or the service layer and can be committed and rolled back based on the outcome of each step. So it's not a problem. You can just put an transactional annotation and everything can happen in that particular method only, making all these things as a child transactions. If you don't understand this, you can just have a look at the transaction management, the video that we have created for the Spring Boot. Now, if this was a monolithic part, it would have been very easy. But when it comes to microservices, you have a single responsibility principle being followed. And what does single responsibility principle says? It says that each particular service should have its own single responsibility. So each microservice has its own DB and another service should not interact with the DB of that particular microservice directly. So these transactions becomes distributed. Why? Because now each of them are going to have their own databases. So now this is order DB, then this is inventory DB, and this is going to be the payment details DB. For a particular client, there might be multiple payments and they can have multiple payment methods in which you can store in your tables also. So that can be there in this particular DB. Now you as a client adds the product and goes to buy it on a particular website. Now the order is created. The item stock has to be reduced by 1 since you are buying that product and the payment is successful. In the monolithic architecture, all are going to have single DB. And if any of this step fails, so payment fails, the inventory should go up again by the amount and the order should be failing. So all this happens in a particular same class, business layer or the method, and hence any step fails, the transaction is completely rolled back. But this is not the case with microservice architecture. For microservice architecture, each step takes place in an individual microservice with its specific database associated with it. So now order will be processed in order service, stocks will be checked in inventory service, and payment will be done with the payment microservice. Now since each step runs in a different microservice, maintaining asset properties is very difficult and complicated. And hence comes the distributed transaction. Now what is distributed transaction? A transaction that is coming across the multiple applications or the microservices becomes a distributed transactions, and maintaining the asset properties across these microservices is very difficult task. So basically there are 2 ways to handle it. The first one is synchronous and second one is asynchronous ways. Now synchronous transaction management can be divided into 2-phase commit and 3-phase commit, while asynchronous we have already seen, that is Saga design pattern. Hey guys, recently we have launched a course covering an end-to-end full stack application using Angular as front end and microservices and Spring Boot as the back end. Also we have used cloud to deploy this application, and we have used CI/CD, that is Jenkins and Argo CD, for continuous integration and continuous deployment. The technologies that we have used is RESTful web services, Spring Boot and microservices for backend, Angular for front end. GitHub we have used for version control system. Also to make the code unit testable, we have used JUnits. We have used Sonar for code quality checks. Also for containerization, we have used Docker and Kubernetes. And to deploy this whole application, we have used AWS and multiple services from AWS. Also, we have used SQL as well as NoSQL, that is MongoDB and SQL. On AWS, since for the SQL we have RDS, we have used those services, and Jenkins and Argo CD for CI/CD pipeline. Also, this is an architecture of the application that we have created where the front end is Angular and the back end is microservices. We have used ALB load balancers, Ingress for routing and load balancing. And we have used SQL and MongoDB for SQL and NoSQL DB management with Eureka Server and all those microservices counterparts. Now this is the CI/CD pipeline. This is the CI/CD flowchart for the application that we have created on local. So this is something, a flow when you create an application in local, push it to GitHub, create a Jenkins pipeline and do the CI/CD using Jenkins and Argo CD. And at the end, deploy the whole code at AWS EKS. Complete description of this course is covered in a very separate video. The link for that video is also given in the description bar below, and also the link to purchase that course from Udemy is also in the description bar below. So please go and check the description for all these links. So let's first see the two-phase commit, which is a synchronous way of distributed transaction management. The two-phase commit is a protocol. So it's just a protocol, the way of doing thing. It's not the code implementation. So it's a protocol to handle the distributed transaction using the two stages. As the name says, two-phase. The first phase is prepare phase and the second phase is commit phase. So let's see the phases here. So this is a client. Client says, I want to place an order. So now what all things will happen in the backend? Order service will come into picture, inventory service comes into picture, payment service comes into picture, and at the end, so client will be responded back as order is successful or order has failed. So these are two possibilities. Now, it seems very simple that client says, I want to place an order. The response comes order placed successfully or order failed. But behind there are multiple things happening at multiple microservices. And at the backend, what happens is one of the service, that is order service, becomes the transaction coordinator in two-phase commit. What happens is order service says we have a request to place an order. So order service acts as a coordinator. So order service says prepare to payment service and inventory service. What payment and inventory service do? They check whether they can fulfill their part of transaction. Means they check whether inventory is there or not. And by reducing it by the required quantity doesn't make the system inconsistent or in negative inventory source. So every service does its own task and see whether this is doable or non-doable. So payment service says, oh, I do not have any payment details. I cannot take the payment. So in that case, it will send, no, we are not prepared. So order service sends a prepare message to all the participants. So once the prepare message is sent, and all the microservice says, yes, they are ready. By reducing the inventory, we are still the consistent state and I have proper payment details with me. We are ready to place an order. So all the participants vote with yes or no. If everybody says yes, then coordinator is good and they say commit. But if any of the participants say no, that means either you do not have the payment details or the inventory after reducing the required quantity becomes negative and the system becomes inconsistent. In that case, if any of the microservice says no, then the coordinator says rollback. So this is a second stage. First stage is prepare. The second phase is commit or rollback. So that is a decision phase. So if all microservice says yes, then only the coordinator says commit. If any of the microservice say no, it sends the abort message to all the participants. And in this phase, the actual changes happens. So you might have kept your inventory reduced by the required quantity, but it is still not committed to database until the commit phase comes. So in the first phase, the prepare phase, you do everything, but you do not commit anything to the database or you do not make any payment request to client. Now, once you have the commit phase, that means the payment service knows that yes, you have the inventory. Inventory service knows that yes, at least if I reduce the inventory, we have payment details with us, we can ask for the payment from the client. So when everybody knows that yes, everyone is ready, then the coordinator sends the commit message to payment service and inventory service. So as soon as the commit comes, the inventory is actually reduced in the database and the payment request is sent to the client. Once the inventory is reduced successfully and the payment service has also taken the payment from the client successfully, then only the coordinator sends to the client that yes, your order placed successfully. Now, even this can die in acknowledgement phase also. So, if the inventory is for any case not reducible or makes the system inconsistent or the inventory service dies or something wrong happens with the network, then the acknowledgement doesn't come to the coordinator. Also, in the case of payment service, if the payment fails, the acknowledgement is not sent to the coordinator. In that case also, the abort or the rollback command is given by the coordinator. So after successful completion, each microservice sends an acknowledgement to order service. If all acknowledgements are received, order service says that, okay, my transaction is complete, client, your order is successful. But if anybody's acknowledgement is missing, then there must be some execution encountered issue. Like for example, any of the service might have crashed or the timeout has happened. In that case also, order service sends the failure notice to client and ask everybody to roll back. Now you can see some very clear drawbacks of this 2PC. The first is a coordination overhead. There's a multiple rounds of communication and synchronization can introduce overhead, and hence complete performance and scalability is reduced in this particular case. So everybody is blocked. What happens is, when order service says, are you ready? So inventory service tries to reduce and see whether it is capable enough to reduce the quantity or not. Also, by that time, payment service, even though it has all the payment details with us, will not be able to take the payment from the client because it does not know whether inventory service has proper inventory or not. So this is a complete synchronous communication. Also, there is a communication overhead until the coordinator doesn't sense, okay, now we all are ready, now you can commit. Till then everybody is blocked. They have done their local part. They have reduced the inventory in local. They have checked and validated the payments, everything. But they cannot ask for payment from the client and they cannot reduce the inventory from the database until the coordinator doesn't say that yes, everything is perfectly fine. So there is a coordination overhead in this particular 2PC. Also, there is single point of failure. If the coordinator, that is order service, dies, what happens? Nobody gets the commit message. No, everybody is left in dilemma whether they have to commit or they have to roll back, whether other microservices are up or running or not. So this is a case of single point failure. If coordinator does not sense the commit or rollback, everybody is in an inconsistent state. Also, it's blocking. So the synchronous has a blocking issue. During the 2PC execution, till inventory service does not make sure that yes, the quantity is there, payment cannot be taken. So this leads to performance issue. And since everybody has to wait, the decision is completely blocking. Now, there is also a case which is handled by 3PC. That is blocking during coordinator failure. So if coordinator fails, you know that there is an issue. Nobody knows what to do next. They have to commit or they have to roll back. So even if the coordinator sends a commit message, but it does not reach to any of the microservice, this leads to the participants being in uncertain condition. So in this case, participant, what they do is they have some timeouts. So they wait for like 2 minutes. If the coordinator does not send you to commit, they understood that the coordinator might have died. In that particular case, in the certain time frame, they roll back. Hence, these particular issues are sometimes, many a times, resolved by 3PC also. In the next video, we'll be seeing some 3PC scenarios. But there are some failure scenarios for 2PC. What are those? The failure scenario includes a participant failed during a prepare phase. So, a participant might have sent, yes, I'm ready. So, inventory service might have sent, yes, I have inventory. But in the meanwhile, inventory service got crashed. So, coordinator did not receive the yes from the inventory service even though you have the inventory. Since it does not get any inventory response from the inventory service, it thought, oh, inventory is not there or inventory service might have down. So, this is a participant failure and this system might fail at that particular time. Also, participant failure occurs during the commit phase. So, what happens is inventory service says, yes, I have inventory, go ahead. Payment service says, yes, I have valid payment details, go ahead. Now, during the commit phase, the inventory was not able to commit and reduce in the database. So, it knows that yes, it has the inventory, but it is not able to reduce the inventory from DB because in the commit phase, inventory service got down. In that case, acknowledgement is not sent to the coordinator. So, coordinator will assume, oh, it was able to reduce, but it is actually not able to reduce currently because of some network or crash failures. In that case, it will again say roll back, sorry. Even though we have everything, we cannot proceed with your order. The third is coordinator failure while sending the commit message. So these were the cases when participant failed during prepare and commit phase. Now third is the case where coordinator itself failed. Now payment and inventory service are sitting there idle thinking what to do. There is a commit or there is a rollback. So what they do is they wait for some time, for 2 minutes says, and then they say roll back. We are not able to handle your orders currently because my order service is down. Also, fourth case can be the network issue. So there can be loss or delays in the communication. So what happens is coordinator says okay, commit. But due to some delays or the network issues, this reaches after 2 minutes. and 2 minutes was the timeout for payment service and inventory service. So they both says, oh, a coordinator is crashed. Even though it is not crashed, there was a network delay. Still they think that they might have died. So what they do is, even though they were asked to commit, they would have rolled back. So this is also where the 2PC might go down. Timeout thus seems to be very critical and crucial in two-phase commit, because participants also wait for the coordinator also waits for the participants. And to prevent the indefinite blocking and the bad user experience where your timer just keeps on running, order is getting placed, we are checking, order is getting placed, we are checking. To prevent such bad experience to users and unresponsiveness of the application, we always used to have the timeouts, which is very critical in two-phase commit. Now a question can be asked, when to choose synchronous or the two-phase commit. So you will choose the 2PC, that is a synchronous way of handling the distributed transactions in the scenarios where there is a very business criticality. So where the success and failures has a significant impact on business. So what it does is, until unless all the participants does not give you the response is not sent back to the client. So client waits till that particular time. So that is synchronous. So when the business is that much critical, for example, in a financial transaction. So it says that there is a financial transaction happening. If it is completed, then only client should say that yes, the financial transaction is completed. So that the data always remains accurate. You cannot be okay with the consistency getting reduced. So whenever you need a great data consistency in this distributed system and you need a strong consistency guarantee with multiple participants, then 2PC or the synchronous communication is good. So if you want to know more about the 3PC, which is also a better version of 2PC, let us know in the comment section. We will create another video for the same. Thank you.